day to everyone. I hope all is well as you will be viewing this lecture of ours. And welcome now to the midterms. And we will be pushing through with our lesson on arguments. I have already sent the module of this section during the prelims, and I hope that you have already read ahead of time this module. So before we proceed with the preliminaries of this section, let's first go through the learning outcomes for this section. We have three. So if your module is open already, if your module is with you, read along with me. So we have our learning outcomes. The first is to understand the concept of open propositions and quantification. So you will find that in that learning outcome, we are now introducing open propositions, though we have already discussed propositions in the previous term. And we are also introducing here quantification. Number two, justify the validity of arguments that involve quantifiers. It's an application of what we have learned in the prelims, checking the validity of arguments. And then the third one, construct proofs. Again, constructing proofs of formulas or statements by applying methods of proving. So there you go. We have our three learning outcomes. And the first section of uh, our the first section is on open proposition. So let's first define what an open proposition is, or sometimes called the propositional function. So it can be called the open proposition or propositional function. So according to this definition, an open proposition is a declarative sentence. So we have learned during the prelims that a proposition is a declarative statement that can either be true or false. So an open proposition is a declarative sentence which contains one or more variables. One or more variables, but it is not a proposition. And three, it produces a proposition when each of its variable is replaced by a specific object from a designated set. So that makes the difference between a regular proposition and an open proposition. An open proposition has no truth value yet until we now have a specific value for the variable present in the proposition. And when we are now to consider the value of the variable, we can obtain the value depending on the universe of discourse being given in the problem. So what's the universe of discourse? It's like the set where we will be obtaining the possible values that we will be injecting for our variable. So let's take the example. The number x plus 1 is an even integer. So this sentence is an open discourse. Is an open proposition. Why is it an open proposition? Because this sentence is not true, it's not also false. We don't know the value yet or the truth value yet of this sentence because we don't know what specific value we will be using for the variable x. So similarly, the second example, we have 2x plus y is equal to 5 and x minus 3y is equal to 8. So we have there two variables, x and y, but we don't know their values. Therefore, we don't know whether that sentence is true or false. And we cannot declare its truth value unless we have the specific value for x and y. So the other examples will also be similar. in the third example, we have three variables. We have x1, x2, and x3. And the open proposition is x1 squared plus x2 squared plus x3 squared is equal to 14. And then when we now go to the fourth example, x is a rational number. Again, we don't know the value of x, so we cannot give the truth value of the sentence. And then number 5, similarly, y is greater than 5. We have only one variable. For number 6, we have two variables, x plus y is equal to 5. While for number 7 and number 8, we may not be referring to numbers, but for number 7, we have example, x climbed Mount Everest. So we don't know who that x is. Okay, maybe siya yung x ninyo. And in number 8, we have he is a lawyer and she is a scientist. We don't know who that he is, and we don't know who that she is in that given sentence. Okay, so this note here is just mentioning to us that for numbers 1 to 6, we can use the set of integers, while for proposition 7 and 8, as I have given earlier, we may refer to some people involved in the sentence. And then, since an open proposition is also known as a propositional function, it means that an open proposition can be denoted using a functional notation. And a functional notation will be having capital letters for the function name itself, and then we have the literal variables or the variables involved in the open proposition. We have some examples here. Let's say p of x. Okay, x is the variable, p is the function. Then this functional notation can denote x is a rational number. So ano lang yung sinasabi rito? Parang yan lang yung representation. X is a rational number. We can denote it as a function, p of x. X is the variable, p is the function, that is, x is a rational number. And then the second example, we have the function is q, and then we have the variables x and y, which can now be described as x plus y is equal to 5. So this is now your function, x plus y is equal to 5. The third example, you have your function is r, your variables are x1, x2, x3, where this function can now be denoted as x1 squared plus x2 squared plus x3 squared is equal to 14. Next, regarding the variables, the variable for an open proposition must be a binding variable to make it as a proposition. So to change an open proposition to a propositional or a propositional function into a proposition, each individual variable must be bound. Okay? Or the value of each variable must be a clear or a precise or a discrete value. And there are two ways of doing this. The first one is by simply assigning a specific value for each of the variables given. So for example, if p of x is the function and this function is denoted as x plus 1 is an even integer, so we can assign a value. So in this case, we are uh, now saying that we are assigning the value of x is equal to 1. So if x is equal to 1, or we can denote that as p of 1, meaning in the function p, we are assigning x is equal to 1, then if you now substitute x equals 1, 1 plus 1 is equal to 2, 2 is an even integer, then you now find the truth value of the proposition. So from an open proposition, we now have a specific value for x equals 1. We get a truth value. Therefore, this now becomes a proposition. Another example, if we have q of xy, so our function is q, we have two variables xy, and this is represented by 2x plus y equals 5, and x minus 3y is equal to 8. So we still have our conjunction. We still have our conjunction. We still have our conjunction and okay. So if we will now be assigning our specific value, let's say we can have x is equal to 2 while y is equal to 1. So in functional notation form, q of 2, 1, x is 2, y is 1. So if you now substitute that in your function given, your x is 2, 2 times 2 is 4, your y is 1, 5 is equal to 5. Therefore, this will be true. And your x is 2, your y is 1, 2 minus 3 is minus 1. Minus 1, is it equal to 8? No. So this is false. We are using the conjunction and in our truth values. So if we have our conjunction and, both propositions must be true to make the entire proposition true. Since one is false, then the entire proposition is false. Therefore, if x is 2, y is 1, then q of 2, 1 is false. Next, the third example. If r of x1, x2, x3 represents x1 squared plus x2 squared plus x3 squared equals 14, then if we now assign our values for x1, x2, and x3 as 1, 2, and 3 respectively, then our proposition is true. Okay, so why will that be true? Because if x1 is 1, so we have 1 squared plus x2 is 2, so we have 2 squared, x3 is 3, we have 3 squared, and 1 squared is 1, 2 squared is 4, 3 squared is 9. So that's 1 plus 4 is 5, plus 9 is 14. So we have 14 is equal to 14, making now our proposition to be true. If the value of x1, x2, x3 are 1, 2, and 3 respectively. Okay, so that's the first type. You can assign a specific value for the variable. Another way of quantifying your open proposition is by quantification, or another way of converting your open proposition into a proposition is by quantification. And under this, we will have two types of quantification. We have our universal quantification and we have our uh, existential quantification. So for the universal quantification, we now use this symbol here. Okay, so this is very important. We have the inverted letter, capital letter A, that is read as for all, and then it's followed by our variable x, And then we have our functional notation, p of x. So this is for all x in px. And if we want now to consider the truth value of our preposition based from this universal quantification, so from the quantifier for all, this proposition will be true if it satisfies, it is being satisfied by all possible values of x depending on what universe of discourse is being described in the problem. Okay, so did you get that? So for an open sentence px with variable x, the sentence for all px being read as for all x in px and is true precisely when the truth set for px is the entire universe, meaning every element in your universe of discourse will satisfy the function given. Okay? And there are similar phrases for that quantifier. So for all x such that, for every x such that, for each x such that. Pare-pareho lang yung meaning nito. Lahat yan denoting or interpreting the notation for all x. Okay? So, for all x. Some examples. Let px denote x squared plus 4. X squared greater or equal to 4. So, our variable here is x. Our function is x squared greater or equal to 4. And according to this, we are now setting, so it is given in the problem that the universe of discourse is the set of real numbers. So your capital R there is being represented by the set of real numbers. And if we want now to consider the truth value, so this is your px, which is denoted by x squared is greater or equal to 4 is your open proposition. So if we will convert this into a proposition using the universal quantifier, we are now saying that our x must be for all possible real numbers. Okay. So if we want now to examine the truth value of this one for all. So your proposition becomes true if for each, for all, for every value of x. So in this case, for any real number, when you substitute it in your proposition, it must always be true. You have x squared is greater or equal to 4. So ano yung sinasabi dyan? If you substitute any real number in x squared, for this proposition to be true, each value of x when substituted here must always be greater or equal to 4. Okay? So it also means that if you want now to make, or if you want now to determine if your proposition is false, this proposition is false, you just need one value of x to violate this proposition. You just need one. So in other words, we are looking at the universe of discourse as the set of real numbers. So if we can just find one real number that will not satisfy this inequality, then the entire proposition will be false. So that is what we call a counterexample. We need to find a counterexample. And in here, you will find that if you now set x is 1 is a real number. Okay, 1 is a real number. You substitute it here, 1 squared, is it greater or equal to 4? The answer there is no. Since if x is equal to 1, the x equals 1 makes this proposition false. Therefore, this proposition is not true for all real numbers because we found x equals 1 is violating this. You can have other counterexamples, but we just need one. We just need one counterexample to make the entire statement false. Another value that will make this statement false is, let's say, x equals 0. 0 squared is not greater or equal to 4. Okay? So that makes now our statement false. Second example, our proposition is p of x represented by x squared greater than 0. This time our universe of discourse is the set of positive integers. So we have the set of positive integers. So I hope you still remember the notations being used here. So let's just have a quick review there. If we are using capital letter R, we have set of real numbers. We have capital letter Z. We have the set of integers. We have capital letter C. We have the set of complex numbers. Okay. Anyway, as we encounter other notations later on, we will be introducing them. So if you have a positive sign above the notation, that means you are considering the set of positive real numbers. Like in this case, you have the universe of discourse is the set of positive real numbers. And our quantifier is the universal quantifier for all x, px. For all x, px. Okay? So if you will now think of this, pag sinabi natin integers, these are the whole numbers. So if we check the set of positive integers, if you get any positive integer, substitute it here. A positive integer, you square it, it would still be positive. And any positive integer squared will be greater than 0. Therefore, the truth value of this proposition will now be true. So from an open proposition, we now use our universe of discourse based from a given set. I mean, we use a universal quantifier and based from a universe of discourse, we now determine the truth value of the proposition produced. So from an open proposition, we now have a proposition. So a proposition is a declarative statement that can either be true or false. So the second type of quantifier is what we call the existential quantifier. So the first one is the universal quantifier. The second one is the existential quantifier. And for the existential quantifier, we now use the inverted capital letter E as the symbol. So this is now read as there exists an X such that Px. So there exists an X such that this value of X will satisfy, or this value of X will be used in the function given. And then from there, you again check the truth value. Okay, let's just compare. What's the difference of the universal quantifier and the existential quantifier? So for the universal quantifier, for the proposition to be true, all the values in your universe of discourse must satisfy the condition in the proposition or in the function. While for the existential quantifier, you just need one value in the universe of discourse to satisfy the given function. Is that clear? For the universe of discourse, each and every or all the elements in your universe of discourse must satisfy the given function. Okay? So let me give an example. Uh, let's use your section. Uh, let uh, let px be the students in discrete math that will uh, still enroll during the second sem. So, if during the second sem, all of you coming from the first sem would still be enrolled in the second sem, then that now becomes a true proposition. But if one of you decides to shift or decides to change course, then that statement becomes false. Did you get that? Okay. And then for the existential quantifier, you just need one to make the the proposition true. Uh, so if we will give an example, maybe we can have the example given here. But before we proceed with that, there are other uh, equivalent for the form there exists. So there exists an x such that there is an x such that for some x there is at least one x such that some x is such that. Okay, so let's have this example. Let px denote the function x plus 75 is equal to 80, where our universe of discourse is the set of positive integers. Our universe of discourse is the set of integers. So, to make now our proposition true, since our quantifier, is the existential quantifier, it means we just need one possible value of x to be substituted in this equation to make this equation true. And since we are looking at the set of positive integers, we know clearly that if x is equal to 5, this equation will be true. Since we were able to find a possible value of x that satisfies this equation, then the proposition now becomes true. So that's the existential quantifier. We just need one value from the universe of discourse to satisfy the given condition. While for the universal quantifier, we need all the elements. We need all the elements in the universe of discourse to satisfy the given condition. Okay? And it may also happen that we have a combination of two quantifiers involving two variables. So in general, if we have our proposition P or if we have our function P with variables x, y, okay, then we have the following possibilities. We can have for all x, for all y in pxy, or we can have for all x there exists a y, or there exists an x for all y, there for all y, for all x, for all y, there exists an x, there exists an x, there exists a y, there exists a y, for all x, there exists a y, there exists an x. Okay, so you will notice here that it is very significant when we look at the positioning of the variables in terms of how the quantifiers are used. It means this is not commutative. It therefore means that, uh, like in this case, look at this. For all x, for all y is not the same as for all y, for all x. And when you want now to consider the truth value, if you want now to consider the truth value of the proposition involving two variables and two quantifiers, according to this, we must always work from left to right. We must always work from left to right. So we have two examples here. Let's just look at these examples. So the first example is for all x, there exists a y. The proposition or the function given is x plus y is equal to 5. And then the second example is there exists a y for all x. And again, the function given is x plus y is equal to 5. The answers are given here already, but let me explain the answers. The first statement is true. The second statement is false. Why? Let's explain that. The first example is true. The second example is false. Okay, so for the first example, we have for all x, there exists a y, x plus y is equal to 5. So by the way, so here the universe of this course is not given. But it is implied that, uh, I forgot to mention that earlier, but it is somewhere in your notes that normally the universe of this course can be given implicitly. Pag sinabing implicitly, pwedeng hindi siya nakastate doon sa problem, pero implied kung ano yung pinanggagalingan niyang value. But there will also be cases like in the previous examples na nakuha natin, yung set of integers, set of real numbers, yun. Very explicit. So, very clear na binigay. So, just in case hindi binigay, like in this example here, then we can now use, so for this one, we can use the set of real numbers. Okay? We can use the set of real numbers as our basis. Okay, going back to this one. According to the answer there, this proposition given these quantifiers will be true. Okay, will be true. So why is that so? So let's explain. So let's go back to this proposition. So we have x plus y is equal to 5. We work from left to right. So we first look at for all x. So, ano yung sinasabi dyan? Yung value ng x, you can use here any real number. Any real number. So, let's say 1, maybe you can use minus 2, maybe you can use 0. Let's say you can use, pag sinabing real number, any number, di ba? So let's say you have 3 and so on. Now, according to this quantifiers given for all x, there exists a y such that it must satisfy this condition. So for all x, so what will happen there? Isn't it that if you substitute a specific value of x here, there is a possible value of y, so that when you add the value of y to the initial value of x, you will get 5. For example, if x is 3, if x is 3, your y is 2, so that 3 plus 2 is equal to 5. If your x is 0, 0 plus 5 equals 5. If x is minus 2, your y must be 7 because minus 2 plus 7 is equal to 5. So you will now find that for each value of x that you use, you can always find a possible value of y to be paired with that x so that this condition is satisfied. That's why this entire proposition now becomes true. For each possible value of x, you can find a unique, or there exists one value of y, which is also a real number, to satisfy this equation. That's why the statement is true. How about the second? According to your module, this statement is said to be false. Why? Why is it false? Let's explain. We work from left to right. We work from left to right. So, what does this mean? Remember, our values of x and y are coming from the set of real numbers. So what we are now saying here is there is a value for y that can be paired for all x such that those chosen values should satisfy this equation. Again, what is the meaning of this section here? There exists a y which will be paired for all x that will now satisfy this. Okay, there exists a y. So for example, if we set y is 3, so this is telling us that if, let's say, you choose y is 3, you can pair 3 to all real numbers represented by x. Let's say x1, x2, x3, etc. So that when you get 3 plus x1, it will be equal to 5. When you get 3 plus x2 is equal to 5. 3 plus x3 is equal to 5. And clearly, that statement will be false, right? So let's say if x1 is 1. Let's say if x2 is 2. Let's say x3 is 3. Let's say x4 is 4, and so on. Okay? So, we must exhaust, in this case, ang sinasabi niya dyan, all possible real numbers must be paired with 3 and must satisfy this equation x plus y equals 5. And that will be impossible. Well, it's true that if x is equal to 2, 3 plus 2 is equal to 5. But that is not satisfying the statement that should now be true for all possible values of x. Okay? So that should be false. Again, why is again the statement false? Because you cannot find a single value for y that will be paired to all the values of x to make x plus y is equal to 5. Okay? So the statement is false. But if you will now revise this, so let's say you now make this as there exists a y, there exists an x for x plus y equals 5. Do you think this will now become true? Yes, because you can choose one value for y, you can pair it with another value for x to give you x plus y is equal to 5. Example, if I choose y is 7, x must be minus 2. So that 7 minus 2 is 5. If my y, let's say, is 3, then my x must be 2 because 3 plus 2 is equal to 5. Making now this to be true. Okay? So again, when there are two quantifiers and there are two variables, you always work from left. You always work from left to right. Okay? So there you have it. Another example here is consider for all x, for all y, x is a real number, y is also a real number. So if x is a real number and y is a real number, then xy, or this is x times y, must be an element of a real number. So what are we looking at here? We're just looking at the closure property. So ano lang yung sinasabi dyan? If you get a real number x, multiply it by another real number y, the result must be a real number. And that will be true. That will be true. Because if you get a real number multiplied by a real number, the result will always be a real number. Okay? So for this time, I'll give you this homework. Well, this will not be submitted yet. Okay? You can just practice solving this problem and maybe we can discuss the solutions of this in our next meeting. So for this time, we can stop here. Then we can just proceed with the others next time. Again, as you find the homework problems here, please do this on your own. Practice solving them. Then we will discuss the solutions of this in our next meeting. So that will be all for now. See you again in our next lecture meeting. Goodbye, everybody.